Hello, hello. Let us look at section 3.3. This is about power and polynomial functions. There's the link to the textbook section for those playing the home game. So what is a power function? So a power function, it's f of x equals k times x times p. So k and p are both going to be numbers. K is referred to as the coefficient. And then P is the power. It's going to be some known power. And so in this first example here, they give us a whole list of functions. There's a whole bunch of different functions here. And they want us to tell them which are power functions. Now, some of these are pretty straightforward here. So like if you look at f of x equals x squared, that is a power function. And f of x equals x to the third, that's also going to be a power function. Those are pretty straightforward because they're, x's and they have powers, so they are a power function. Now, fun fact, x just by itself can be written as x to the first power. So this one right here, which they call the identity function, that also, in fact, is going to be a power function since x is equivalent to x to the first power. Now, what about just plain old 1? Well, you might have a vague recollection of this little factoid from back in the day, but anything raised to the 0 power equals 1. So if you take x to the 0 power, that will give you 1. So in fact, even just a function where it equals a number would qualify as a power function. The power would just be 0. Now, what about this next one down here? We've got 1 over x. You might kind of sort of remember this sort of thing. If you've got reciprocals, reciprocals come from negative powers. So 1 over x is in fact equal to x to the negative 1 power. Negative powers give you reciprocals, so you just put a 1 on top and you take whatever you have and you put it on the bottom. And you could write this as 1 over x to the first if you would like. And like we were talking about before, if you have x to the first power, that's still just normal x. So far, every single one of these is actually turning out to be a power function. Even if you have 1 over x squared, that is in fact just going to be x to the negative 2 power. Because again, all the negative sign on a power does is it gives you the reciprocal, put a 1 on top and take whatever you have with a positive power. So in this case, x squared, that would be the reciprocal squared function. That is also in fact a power function because you can write it as x raised to some power. In that case, negative 2. Here we've got the square root function. You may have come across this fact before. The square root is actually equivalent to doing the 1/2 power, x to the 1/2. If you were to take a calculator, take the number 9, for instance, raise it to the power of 1/2, or also known as 0.5, that's the same as 1/2. If you were to take 9 and raise it to the 0.5 power, it'll give you the number 3. And the reason is square rooting is actually equivalent to a power of 1/2. So this is in fact also a power function. It's a power function where the exponent is a fraction. And then in a very similar fashion, if you were to do like the third root of x, for example, that's going to be x to the 1/3 power. So every single last one of these, regardless of how different they kind of look on the surface, it turns out every single one of those is a power function. Some of them are maybe, shall we say, kind of obvious, but x to the first is the same as x to the 0 is the same as 1. When you've got reciprocals, those are negative powers. When you've got roots, those are fraction powers. But every single one of those is in fact a power function. Let's see, we have a duplicate here. I don't really need that. I'll just delete this. Okay, which of these are power functions? All right, so for this one, let's look at f of x first of all. You can clean this up because you've got 2x squared times 4x to the third. And if you take 2 and multiply by 4, that is going to give you 8. And then when you're multiplying with powers, remember that like x to the n times x to the m, what you're supposed to do is add the two powers together. So that just means we're going to do x to the 2 plus 3 right here. So what we will end up with is 8x to the 5th. And guess what? That is actually a power function. It has a coefficient of 8, and it's got x raised to a power, in this case, the number 5. Now, g of x is not, in fact, going to be a power function because it's got multiple pieces that are either added or subtracted. G of x is not a power function. That is, in fact, a polynomial. And the poly in polynomial means many. So that is not a power function. That would be a polynomial function. If you have more than one term that's either added or subtracted, you are no longer a power function. Likewise, for h of x, this is also not going to be a power function. The name for this is actually a rational function because it's a ratio or fraction. That is a whole lot more complicated than just 8x to the 5th or x to the 3rd. That is not going to be a power function. Because it's a fraction, that's a different kind of function. Okay, so let's see what else we have going on here. So, identifying the end behavior of a power function. So, there's basically a couple of different things that can happen. And the thing to look out for is, first of all, do you have an even power or do you have an odd power? That's the first thing you want to check. And then the other thing you want to see is, do you have a negative constant or do you have a positive constant? So the value of k, is that a positive number or is that a negative number? And again, just to remind ourselves, the formula for a power function, the general format, f of x equals k times x to the p. So we're basically interested in what is the sign of the k value in front, and then what kind of number is p? Is it an even number or is it an odd number? Now, if you have an even power, either this kind here or this kind here, the thing to notice is that for the even powers, both ends are going in the same direction. Either both of them go up or both of them go down. So for even powers, for an even power, the ends are going to go in the same direction. On the other hand, if you have an odd power, those are going to go in the opposite direction. So like with this one, the left side goes down and the right side goes up. Here, the left side goes up and the right side goes down. But the big takeaway from either of these is that the ends go in opposite directions. One goes up and one goes down. Now, as far as the constant is concerned, if it is positive, here's the thing to know. What do these first two have in common? If we look at this, you'll notice the right side is going up for each of these, whereas if it's negative, the right side goes down. And that's how you can figure out what is going on with the right side. If it's positive, the right side goes up. If it's negative, that means that the right side goes down. So once you figure out what the right side does, you can then figure out what the left side will do, because depending on if it's odd or if it's even, even tells you that the left side will do the same thing. Odd will tell you that the left side will do the opposite of whatever the right does, which is kind of similar to how my son and daughter behave sometimes, where if one of them does one thing, the other one will often want to do the complete opposite of that. So yeah, there you go. Anyway, so they say describe the end behavior of the graph f of x equals x to the 8. So here's what we know. So it has an even power. And the other thing to know is that it is positive. There is no negative sign in front of it. So it is an even power and it is positive. So what we will do first is we will say, okay, first look and see what happens if it's positive. So start right here. Number one, it's positive. That means the right goes up. As for the second thing, then look and see if it's even. If it's even, that means that the left is the same. So then what that means is that the right goes up and then the left goes up. And actually, I'll tell you what, why don't I put the left on the left side? The left goes up and then the right goes up. That's how you can figure that out. Now, what I have yet to talk about is all this kind of, shall we say, gobbledygook down here. This is sort of the formal mathematical notation to describe the end behavior. And at first glance, you may look at that and be like, bro, I don't know what that means. But let me unpack this for you to help you make sense of it. So first off, every graph has a left side and every graph has a right side. No matter what, a graph has a left and a graph has a right. So the way you say in math speak, the left side is you would say, okay, x is going to negative infinity. Because fun fact, the left side of the graph is where all the negative x values live, yes? And if you went that direction forever, that would be where negative infinity lives. And then you have the right side, and the right side will always be x goes to infinity, positive infinity. Because on the right side of a graph, that's where all the positive x's live. So this is just math speak for left side. And this is just math speak for the right side. And like I mentioned, if you're describing end behavior with symbols, you will always have a left side and a right side. So you would always write both of these things down because every graph will have a left side and a right side. Once you've figured out whether it goes up or down, you then say f of x and then tell them where it goes. And you do the same thing down here. You say f of x and you tell it where it goes. Because it's going up, values that are up are positive. So for both of these, since they are up, you would put positive infinity. So this would be positive infinity, and this would be positive infinity. So then the actual answer, the end behavior that they are looking for, We'll do this in black. You would say this, and you would say this. And the only thing that ever changes is the part I put in red, where you say where f of x goes. It will either be negative infinity or positive infinity. And again, you have to interpret it based on, is it positive or negative? Is it even or odd? But you will always say x goes to negative infinity. You will always say x goes to infinity. You will always say f of x goes somewhere for the first one. And you will always say f of x goes somewhere for the second one. That is always going to be true. You just have to figure out, is the left side going up or down? If the left side goes up, you put positive infinity. If the left side goes down, you put negative infinity. Same for the right side. If it goes up, you put positive infinity. If it goes down, you put negative infinity. So that's sort of in math speak what all of that means. Okay, here is another one. So they say, describe the end behavior of the graph. F of x equals negative x to the ninth. So what I know is that it is negative. And I also know it's a 9 is the power, so that's an odd power. And then without doing much analysis, I can already write down this much. It's always going to have f of x equal, it's always going to have x to negative infinity. It's always going to have x to positive infinity. That's in plain English, that means left and right. Meanwhile, we're always going to say f of x does something. We have yet to decide what, but it's going to do something. We're just waiting and seeing what. Negative. What does negative tell me? That tells me that the right goes down. For negative values, the right side goes down. So here's a negative constant. The right side goes down, the right side goes down. That is what both of those graphs with a negative constant have in common. The other thing that we know, the power is odd, which means the left will be the opposite. Since we have figured out what the right is doing, you kind of have to know what the right is doing before you figure out the left. So since we know the right side's going down, that's why I like to start with the right side. Since we know the right side goes down, that just means that the left side is going to go up. That's the opposite of down. So then the left side goes up. Up is positive infinity. The right side goes down. Down is negative infinity. And there you have it. That would be what the answer would look like. That's the answer that we are going for. Okay. So that is just describing the end behavior of power functions. All right, let's see what else we have. Describe in words and symbols the end behavior of negative 5x to the fourth. So I've kind of been doing both of these all along the whole time, but we'll just go ahead and do this again here, just for good measure. So k is negative 5 in this case. That's the coefficient in front. Big factoid about this is the fact that it is negative. The power p is 4. And the noteworthy thing about that is that the power is an even number. So it's negative and it's even. So what does it mean if it's negative? Well, negative tells me the right goes down. So they tell me to say it in English. So there you go. It's right and down. If it's even, that means the left is the same. Whenever it's even, that means that it's the same as the right. So the left is the same. Well, since we know what the right side is, that just means that the left is also going down because it has to be the same as whatever the right is doing. So if you were to say it in plain English, That's maybe not grammatically correct, right down, left down, but that's essentially what you're trying to get across in English. Right side goes down, left side goes down as well. If we're going to do this in symbols, here we go. X goes to negative infinity. This is the left side. X goes to infinity. That is the right side. Every graph always has a left side and a right side. So without even thinking, you would just write both of these things down, like no matter what, because it's always going to be there. There's always a left side and a right side. And then you're always going to say f of x goes somewhere, because, that's, if you have a graph, it's got to go somewhere. And then what did we say earlier? Down and down. Down means negative infinity. So the only thing that ever changes from one answer to the next is just this last little bit. This here and that here. That is the only thing within all these symbols and notation that ever changes or does anything. And so since we've decided it's down in both cases, we just put negative infinity because that's math speak for down. Because negative numbers are down on a graph. So there you have it. There it is in words and in symbols. Okay, what else do we have going on here? Now we're going to talk about polynomials. And so polynomials are basically just a whole string of power functions that are either added or subtracted with each other. So each chunk separated by a plus sign or a minus sign is called a term. So each product here, that is called a term. That is the term for that block. It's called a term. There you go. So which of these are polynomials? Let's look at f of x first in this example. So they give us 2x to the third times 3x plus 4. If you multiply this out, 2 times 3 is 6. You could call that the first power if you wanted to. The third power plus the first power is going to give you a grand total of the fourth power. Because if you multiply all those together, that would be 4 different x's. So if we simplify this function, that would be what it would look like. 6x to the fourth plus 4. And fun fact, that is a polynomial. That's a kind of standard garden variety polynomial right there. That is indeed a polynomial. One thing I should mention, as I have not done so yet, there is one catch about polynomials, which is that you do need to have you must have whole number powers. So unlike the power functions, that basically means you can't have negative or fraction powers. That is a very crucial distinction that is different about polynomials compared to power functions. You can't have negative or fraction powers. So let's look at the next function they gave us, which is g of x. And they tell me that's negative x times x squared minus 4. Kind of like the previous one, we would want to use our distributive property to simplify this. A negative times a positive will give me a negative result. So that's going to be negative. This is 1x. There's 2 more. That'll be a grand total of 3 of them. X times x squared means you've got x times x, which is x squared. So altogether, there would be 3 of them. Negative times negative is positive, and that'll be 4x right there. And then, fun fact, that is also a polynomial. It has whole number powers. It's got multiple terms added or subtracted, as the case may be. But that is also a polynomial. That's just a standard garden variety run-of-the-mill polynomial there for you. Now, for this last one, h of x, you've got 5 square root x plus 2. We had this conversation earlier. You could call the square root of x, you could write it with a power, which would be 5 times x to the 1/2. And as we mentioned, you cannot have negative powers, and you cannot have fraction powers in a polynomial. So then what this means, this is in fact not a polynomial. With polynomials, you have to have powers that are whole numbers or fractions. Or I'm sorry, that are whole numbers. You cannot have fractions, and you cannot have negative numbers as your powers. Okay. Why did I say not a polynomial? It's just not a polynomial. There we go. Okay. So other terms, terminology regarding polynomials. We often rearrange polynomials so that the powers are in descending order. And when you write it in this way, that's called its general form. And so then there's something known as the degree. The degree is the highest power of x. That is a useful term to be familiar with. We're going to use it a lot. So whenever I say the word degree, what that means is it's the highest power of x. There's also this thing known as the leading coefficient. And all the leading coefficient is, the coefficients are the numbers multiplied by x in the front. So then the leading coefficient is just going to be the coefficient with the highest degree term. So it's the coefficient with the highest power term. Coefficient with the highest power term. And the reason it's called the leading coefficient is if you write it in sort of the proper way where the highest power is in front, it's the leader, that's kind of the preference. If you write it so the highest power is in front, then the leading coefficient will be the leader because it's the one that's in the front. Okay. Identifying the degree and leading coefficient of the polynomial function. So we got a bunch of polynomial functions here. A lot of the terms are sort of jumbled up in the wrong order. So they want us to tell them the degree, the leading term, and the leading coefficient. So let's start with f of x. And the first thing we'll do is we will rewrite f of x. And so the plus and minus signs will separate each of the terms. And the plus or minus sign is attached to the number directly behind it. And so if it's a minus, that means you have a negative coefficient. And if it's a plus, that means you have a positive coefficient. But the plus and minus signs let you see the boundaries from one term to the next. And the plus or minus sign is attached to the number directly behind it. So if we were to rewrite this function, f of x, so that it's in the proper order, we would write negative 4x to the third plus 2x squared. And then this is positive 3. They don't come out and say it, but because it's positive, we would need to put plus 3 there because there has to be a plus or minus sign separating one term from the next. You don't want to just write 2x squared 3 because that would look like it means to multiply. So the degree. And so once we've got it written in the standard form, pretty much this first chunk is all we really care about. We frankly could kind of care less about everything behind it because we're just going to follow the leader here. So the degree is going to be 3. That's just the highest power of x. The lead term is the whole thing I've highlighted, negative 4x to the third. And then the lead coefficient, that's just the negative 4 that's parked in the very front. So that would be the degree, leading term, and leading coefficient of that polynomial. Next up, we have g of t. And this one conveniently is actually already in the standard general form, 5t to the 5th minus 2t to the 3rd plus 7t. It's already arranged so that the powers are in descending order. So we don't have to do anything with it to change it around. So this right here, the 5t to the 5th, that is your leading term. The degree is 5. The lead term is 5t to the 5th. And then the lead coefficient is also 5. There's nothing that says that they have to be different numbers. They can be the same number. So there you have it. Last one from this set is h of p. Like before, we want to arrange these so that the powers are in descending order. And again, remember, if it's a straight up p, that means the power is a 1. If it's a straight up number, that means the power is a 0. The numbers always go last. Anything with just a p or an x or a t and no power, that's always going to be second to last with any just constant number behind it. So if we arrange this in descending order, negative p to the 3rd would go first. Like before, we would need to put a plus sign here, plus 6p. And finally, minus 2. The leading term is right here, negative p to the 3rd. So we would say the degree, the highest power of x, that would be a 3. The lead term, that would be negative p to the 3rd. Now the question is, what would be the lead coefficient? Well, if it's just a straight negative sign, you could write that as like -1 times p. So if there's ever a polynomial where they don't have a coefficient, that just means the coefficient is a 1 by default. If it's a minus, that would be a -1. So the leading coefficient would be -1. It's not just a negative sign because you do need an actual number. So the number you can multiply as a coefficient that won't actually change anything is 1. All right, we got 4 slides to go here. Let's see what else we have going on. Identify the degree, leading term, and leading coefficient of the polynomial. All right, so here is the first term, here is the second term, here is the third term, and here's the fourth term. And what we need to do is put them so that the powers are in descending order. Negative x to the 6th plus 4x squared plus 2x minus 6. The leading term is this one right here. It's the leader here in this little polynomial train that we got going on here. So the degree is 6. Lead term is negative x to the 6th power. And then like before, if it's a minus, the leading coefficient would be -1, because you do need a number of some kind, not just a negative sign. So there you go. That would be the degree, lead term, and lead coefficient of that polynomial. Identifying the end behavior of this polynomial. So they give us this polynomial and they say express the function as a polynomial in general form and determine the leading term, degree, and behavior of the function. All right, well, what we need to do is take the formula they give us and simplify it. This kind of thing should look familiar because this is a job for FOIL. We're going to do first, outside, inside, last. We're going to multiply it out. So when we do that, what do we get? X times x is x squared x times 4 is plus 4x. Negative 1 times x is minus 1x. Negative 1 times 4 is negative 4. That and that are like terms. So we can put that together and get x squared plus 3x minus 4. That's what you get when you multiply those things. Don't forget that there's also negative 3x squared hanging around in the front. Now we're ready to do the distributive property and multiply by this guy back here. So if we do that, we're going to end up with f of x equals, what is that? Negative 3, because there's really no number there. X squared and x squared is going to be x to the 4th. You add the powers together. Negative 3 times 3 for the middle term is minus 9. X squared and x would be x to the 3rd. There's 2 and then 1 more, so that's a total of 3 x's. Then negative 3 times negative 4 is plus 12. And then you carry along the x squared along for the ride, and there you go. That is the polynomial in standard form. We are interested in the leading term, which is this right here. And like we were doing before, we're going to identify the degree, which will be 4 the power of the x. The lead term, that's what I have highlighted, negative 3x to the 4th. The lead coefficient, that's just the number multiplied in front, which in this case is the number negative 3. Okay, so that is that one there. Determining intercepts. So here is how you can find the intercepts. And here they were very nice to us because they gave it to us in the factored form. The next one, it is not in factored form, which is going to be a little more challenging. But here's how we can find the intercepts. You find the x-intercepts, solve for each factor equal to 0. And when you've done factoring in other math classes, I imagine you've done this kind of thing before. So like you've got each of the things in parentheses, x minus 2, x plus 1, x minus 4. You've got each of the different factors in parentheses all by themselves. And what you do is you make a little equation where each factor equals 0. And the reason you do that is because if you're multiplying stuff and get 0, that means that one of those has to be 0. And this will let you find x values. That will be the x-intercepts. So this is going to give you x equals 2. This is going to give you x equals negative 1. This is going to give you x equals positive 4. Now these are intercepts. You want to write them as points. And what this means is that you have 2, 0, negative 1, 0, and 4, 0. Those are the x-intercepts. There happen to be 3 of them. And one of the ways you can tell those are x-intercepts is because the variable you solved for was x. For the y-intercept, you want to plug in 0 for x. So I'm going to take this formula and I'm going to do f of 0. And that's going to be 0 minus 2 times 0 plus 1 times 0 minus 4. So every x gets replaced by a 0. You plug it in and you work it out. 0 minus 2 is the number negative 2. 0 plus 1 is 1. 0 minus 4 is negative 4. If you multiply those 3 numbers together, you will obtain 8. So f of 0 equals 8, meaning you have the point 0, 8. That is the y-intercept. So that is how you can use a polynomial to find the x and y intercepts. To find the y-intercept, plug in 0 for the x and then just work it out. If you want the x-intercept, and it's possible to have more than one, what you do is you set the whole function equal to 0 and then solve for where each factor would give you a 0. These are points, remember. So the x-intercept is going to have an x value with a y of 0. The y-intercept will have a y value and an x that is 0. Now here they give us this. They say 2x to the third minus 6x squared minus 20x. Let's find the y-intercept first because that's usually a lot easier. You plug in f of 0 and see what you get. 2 times 0 cubed minus 6 times 0 squared minus 20 times 0. Fun fact, 0 to any power, 0 multiplied by itself a bunch of times, guess what? That will always be 0. So this is 2 times 0. This is 6 times 0. And that is 20 times 0. And again, anything times 0 is 0. So this is 0 minus 0 minus 0. And fun fact, that just means you get 0. So f of 0 equals 0. That means the y-intercept is 0, 0. Okay. How about the x-intercept? I'll show you two ways you can approach a problem like this. The first is factoring. And if you are a bit rusty on factoring, I might encourage you to go back and review some of the tricks for how to factor something. This one has a greatest, well, so let's see. We're going to solve for where this equals 0. So we got 2x to the third minus 6x squared minus 20x. This has a greatest common factor. You can divide a 2 and an x from each of the terms. And if you do that, this will leave you with x squared. That will leave you with minus 3x. That will leave you with minus 10. So every one of them has one fewer x. And then I have divided all the coefficients by 2. So instead of 2, 6, and 20, I now have 1, 3, and 10. Now you can factor this thing. Here's a minus 10. So set up your parentheses here. You're going to have an x and an x. Minus 10, that's probably going to be like 5 times 2. And if you do negative 5 plus 2, that would give you negative 3 if you add them together. And if you do negative 5 times 2, that will give you negative 10. So then you take each of the factors, now that it's factored, and you take each one and solve where it equals 0. See where 2x equals 0, see where x minus 5 equals 0, see where x plus 2 equals 0. This we divide by 2, you get 0, which is actually the exact same one as that, because fun fact, those are going to be the same point. Here you add 5. Here you subtract 2. So we've got 0, 5, and negative 2. So the x-intercepts, there are 3 of them. You're going to have 0, 0, 5, 0, and negative 2, 0. And when you solve for an x-intercept, you solve for an x. So the 3 numbers we found are the x values. And by default, the y's are all going to be 0 because that's what we're trying to find, is where the y value is 0. That's kind of what it means when they ask for an x-intercept in the first place. Now, if you're a tad rusty on factoring, here's what I'm going to show you. So let us break out the graphing calculator here. And let's see, I'm going to go to the y equals menu. We've used it before some to make a graph. And let's see here. If I remember right, it was 2. There's your button for X right there, 2X. Let's see, that was to the third, so 2X, raise that to the third. I'm still in the exponent right now, so I need to arrow over and get it over here. Then what was it? Minus 6X squared, here's the squared key. And then lastly, it was minus 20X. Okay, there you go. So there's the formula for that. And then I'm going to go to Zoom and pick the standard window. And here you go. It's drawing that. And then from this picture, here's what you can see. There's the value right there at 0, 0. This is what? 1, 2, 3, 4, 5. That's the value at -5 right there. You can kind of count your little tick marks. And then the other value was at what? Well, let's see. I'm looking at it backwards. This is +5 because that's your right. This is -2. That's the other value we saw. This is, yeah, so that's, this right here is +2. This right here is -5. You can also, if you go to second and then the trace menu, you can find the 0. So like if you arrow over here, there it is. All right, I want to be on the left side. Okay, so that's the cursor on the left side. Whoop, oh jeez. No. Insolent machine. All right, try that. Let's try this again. Doing it with a mirror image is really difficult, let me tell you. I would much rather Zoom show me the actual picture you all see, and I can cope with my picture not looking like my mirror image. Okay, so that is the left bound. And then we're going to arrow over, and there is the right bound. And then you can just pick the same spot as your guess, that's fine. And there you go. So it told us what we already knew, which is that it's at the 0.50. And you can do the same strategy to find that one over here. And then you can find the other one right there. And so if you're a bit rusty on your factoring, fun fact, if you know how to draw a graph and know how to find the intercepts, you can just cut to the chase and find exactly what you're looking for from the picture. There are a lot of analytical techniques that we use, but especially, a lot of these techniques exist from a time when graphing calculators were not common. But nowadays, because they're a lot more easily obtained than they used to be, making graphs is not that big of a deal. So you can make the graph yourself, just look at the picture and find the intercept points just directly from the picture. But that's how you would do it analytically with no graph directly in front of you. All right, anyway, that is what I wanted to talk about tonight. So I'm going to stop there. And then once my thing is, whenever it decides to wake up and quit doing this spinny thingy, I'll take the attendance and then we can go.